So let's talk a little bit about matter and how it's found in nature. Typically, the substances we find in nature are mixtures. The substances you see pictured here are all examples of that. Mixtures come in two forms: heterogeneous mixtures, where the composition varies at different places in the mixture, and homogeneous mixtures, which are the same throughout. So, for example, a tea bag has different kinds of tea and different leaves that are spread out throughout the tea bag, but if I sample in one portion of the tea bag, I'm going to get a different composition than I do if I sample somewhere else. By contrast, homogeneous mixtures have compositions which are identical throughout, so no matter where I sample, I get essentially the same composition. And that's important in chemistry because we want to be able to sample substances and be able to say that the results we get are consistent with the substance. Here on the Earth, the simplest building blocks of matter are atoms. They're stable, at least most of them are, and they're pictured in the periodic table, which we'll talk in some detail about a little bit later. You're responsible for knowing the names and symbols for the first 3 rows of the periodic table through argon. And you're also responsible for the elements that are listed in this table, some of which are in that first 36, others are beyond it. But these are common elements that we refer to quite a lot. You can also have pure substances. So, for example, we can extract the caffeine out of coffee and provide you with decaffeinated coffee. And the substance we get that we can take from the coffee can be purified by recrystallization to create a pure compound. A compound is a substance that's made up of at least 2 different kinds of atoms. The point is that the atomic arrangement in caffeine is the same for every group of atom, carbon, hydrogen, and nitrogen, that are present in the compound. By contrast, we can have materials that are pure elements. This is a sample of carbon that's been created by pouring sulfuric acid on a carbohydrate like sugar. Carbohydrates basically consist of carbon and water, although the arrangement is different from that. But if you add a desiccant, something that sucks up water like sulfuric acid, you can remove the water and be left with the carbon, which you see here. All substances consist of atoms of various kinds, and it's important to make a distinction on the microscopic or submicroscopic level. So here we have pictures or cartoons of 4 different situations. In the first situation, we have monatomic, 1 atom species. These might be noble gases. And you'll notice that they're all identical. So that would make this an element existing with only 1 kind of atom. I should point out that the atoms of noble gases aren't red. We're using color to distinguish different kinds of atoms. And you can see that in the second picture, the atoms present are all the same, but this time, 2 are attached together in what we call a molecule. A molecule involves 2 or more atoms that are bonded together by sharing electrons, forming what we call covalent bonds. So in this case, you also have an element, because there's only 1 kind of atom. But this time, instead of having atoms, you have molecules, diatomic molecules, and many elements, such as oxygen and nitrogen, exist in nature as diatomic gases. Others, such as bromine, exist in nature as diatomic liquids, and iodine is a diatomic solid. These are all pure substances, and they're all elements. In the third picture, you see a compound. A compound because it consists of 2 different kinds of atoms. This might be sulfur trioxide, for example. But what you notice about these arrangements is that they're all the same. Each of them has 1 purple atom in the center and 3 green atoms surrounding them. Each of them would be sulfur trioxide. So even though this is a compound, as opposed to an element, it is still a molecule because the atoms are sharing electrons with one another to form these species. And it's also a pure substance because every compound has exactly the same formula. So only the last slide represents a mixture. In fact, a mixture of the species in the first 3 slides. And in fact, because these species are pictured in the gas phase, This represents a homogeneous mixture or solution. All gaseous mixtures are homogeneous because even if they don't start out that way, gas molecules are moving so fast, on the order of 500 to 1,000 meters per second, that's 500 to 1,000 yards per second in our vernacular, they still become homogeneous mixtures very quickly.